Am I muted here? Emily, can you hear me?
Yeah. It's 3 o'clock, so let's get started. I would like to welcome everyone to the third NFIE, National Flood Interoperability Experiment webinar hosted by CUAHSI. This is Emily Jessling. I am standing in for Emily Clark today, who is otherwise occupied. And yes, there are two Emilys that work at CUAHSI. And we're very excited to have David Maidment from the University of Texas at Austin with some of his colleagues who he'll introduce, and also Jim Nelson from Brigham Young presenting today. And without further ado, I will let David take the stage. So please go ahead.
Okay, thank you very much, Emily. So what we want to do today is to provide a more detailed technical description of what we're planning to do with the NFIE. So this experiment arose from the first meeting that was held at the National Water Centre in May, and I attended that meeting and I proposed this experiment immediately afterwards. And it was accepted that because the federal presence of the centre will take a while to increase, that students could come to Alabama this summer and be able to work on things that would be helpful for the water centre. The Water Centre is going to nationally synthesize the operations of the regional river forecast centres that are presently in 13 different locations around the country. And what we're going to do with the NFIE is to work within the framework of CUAHSI and the IRAS partners, which are the Corps of Engineers, Geological Survey, the Weather Service, and FEMA, to be able to build a new centre or new operational hydrology model at the National Water Centre. The experiment will run from September 2014 to August of 2015, and we'll have the Summer Institute that's going to take place from July 1st through July 17th in Alabama. There'll be another webinar in 2 weeks' time to talk about how students can get engaged in the Summer Institute. CUAHSI has a website for the NFIE, so all the information that's available will be presented there. There is a description of the project, past webinars that have been presented, the map access to the NFIE geodata that I'm going to present is accessible there, and the call for proposals is coming soon from CUAHSI. What I want to point out is that we're not trying to produce an operational forecast system. It's a research effort. It's not going to create an operational forecast system. It's not going to produce public forecast information. It's just a research effort. This little thermometer thing on the right-hand side is a set of levels that is used in the federal government to define how ready something is in the path between pure research and complete applications, and we're right down the bottom of that cycle. The goals that have been established jointly with the Weather Service for the NFIE are to answer questions that how can near real-time hydrologic simulation at high spatial resolution covering the nation be carried out using the NHD+, which is a geospatial data set I'll talk about in a moment, or a new generation hydrofabric, which is a framework of data in space and time across the country. How can this lead to improved emergency response and community resilience, and how can an improved interoperability framework that supports the first two goals lead to sustained innovation in the research to operations process? In other words, how can we engage with the federal government and the Weather Service in being able to do this over a significant period of time and not just for this one summer? Now I'm going to present the technical framework in 5 components here. I'm going to say that there's NFIE Geo, a National Geospatial Framework for Hydrology. There's NFIE-Hydro, National High Spatial Resolution Hydrologic Forecasting System, NFIE-River, River Channel Information and Real-Time Flood and Inundation Mapping, and NFIE-Response, which is Wide Area Flood Planning for Flood Emergency Response. And all those are going to sit on NFIE-Services, which is Weather Services for Flood Information. So first of all, what are we doing with NFIE Geo? So we're building this on top of the NHD Plus version 2, which is the synthesis of the National Elevation Dataset, National Hydrography Dataset, Land Cover Dataset, and Watershed Boundary Dataset that's been accomplished over the last 20 years. And there are now 2.67 million reach catchments in the United States of average area 3 square kilometers and average reach length 2 kilometers. And those are going to be the elementary landscape units that we're going to use for the catchments in the NFIE. I have asked the federal government, and this is the Subcommittee on Spatial Water Data, to prepare for the NFIE 9 feature classes that will cover the continental United States. 5 that come from the NHD Plus, which is subwatersheds, catchments, flow lines, water bodies and dams, and the subwatersheds will be the HEC-12 subwatersheds. And then 4 that come from the IRAS partners, which includes USGS water watch points for stream flow, the National Weather Service forecast points and basins. So what you see at the top here is the system that is currently being used by the National Weather Service. The colors represent the different forecast centers. The little drainage areas that you see are forecast basins, and at the outlet of these basins there's a forecast point, and there are 3,600 of those across the country, and that's where the Weather Service issues its forecast now. And we want to supplement that also with the FEMA National Flood Hazard Layer. So those 9 feature classes are being prepared by the federal government, and they're going to be synthesized and made available by March the 31st to support the NFIE. NFIE stands for National Flood Interoperability Experiment. We've shortened it down to NFIE. Our elementary units are these little reach catchments. So the NHD Plus reach catchment, this is one shown here called 5781369, is a single catchment that has a single flow line in it, and those flow lines are networked right across the country. We have intersected those with the FEMA National Flood Hazard Layer and made a little flood response zone that's in each catchment, so that if we can inform the catchment and the streams through flood forecasting, we can show the flood risk zone that's from the flood map associated with that. The catchments are themselves aggregated into subwatersheds. This one here is in the Onion Creek area in Austin. It has 19 reach catchments in it, and this is the base for hydrologic modeling. So to do hydrologic modeling in the normal way that we think about it, we're going to use these subwatershed scale, and we're also using that for flood emergency response planning. The data, a first cut at the data are already available, and if you go to the CUAHSI website, http://www.quasi.org.nifie, you'll see access to this web map. The web map is an ArcGIS online map, and it provides access to data in the quasi-Hydro share system, which is a file-based system developed at the University of North Carolina by David Tarverton from Utah State University and Ray Idezak from Renzi and a bunch of other partners. And you can download the NFIE geodata as we have prepared it so far for any place in the country. We have 12 regions of information accessible here. Actually, the website works very quickly. Now, the data that we are getting from the federal government is mostly watershed boundaries and streams, but it's not the deeper things having to do with soils and geology and things like that that we probably would want to have in doing hydrologic modeling. There is a parallel system that's been developed at Penn State University called HydroTerra, developed by Lauren Leonard and Chris Duffy, that supports information extraction on land cover, geology, NHD, streams, national land cover, soils information, and so on, for each 12-digit HUC unit. And they call these essential terrestrial variables that can be accessed through a website where you can choose the HUC-12 units that you want anywhere in the country. This is a wonderful system that's been developed at Penn State, and we really appreciate the contribution they've made for that. You can get from HydroTerra prototype information for land parcels, streams, lakes, soils, and other matters that will supplement what is in the federal data set that will be coming through the NFIE. The group at Penn State has a system that's illustrated here where you select some HUC-12 units, you clip or extract them, you compress the data, they send you an email, and then you go get your information. So there's a way of accessing detailed information like that. And if you want to go on to the modeling part, there's a thing called the Penn State Integrated Hydrologic Model, which Chris Duffy knows way more about than I do, so I won't attempt to explain this, but if you want to do really detailed hydrologic modeling, this is one of the ways of going about that. And this is some work being done by Jean Yu as a PhD student at Penn State on application of the Pennsylvania Integrated Hydrology Model for areas of Pennsylvania. I'm not using the PIM model to say it has to be the PIM model, just to show that there is a detailed hydrologic modeling system that can be built, or any other actually, from the data that's in the HydroTerra system. Now, how is all this going to come together nationally for hydrology across the country? NFIE-Hydro, this is where the water part is coming in. What we've done so far is just the geo part, just the GIS kind of layers. The NFIE-Hydro is going to be coordinated through a system called WRF-Hydro, the Weather Research Framework Hydro, which is developed at the National Centre for Atmospheric Research by David Gotches. And this is a community-based coupling architecture to look at land atmosphere modelling over multi-scale and multi-physics to deal with precipitation, soil moisture, snowpack, groundwater, stream flow, etc., and to deal with this at a bunch of different spatial scales. There's a whole system that's been built up over a number of years that supports that, and it's got connections to gridded analyses and forecasts, to weather and climate prediction models, to data assimilation, land atmosphere models, subsurface routing, water management, and integrated hydrologic modeling. This is a framework for constructing hydrologic models. It is not itself a model. So the idea is that, for example, RAPID, which is the streamflow information program, modeling system that we're using, gets incorporated into WRF-Hydro as a WRF-Hydro component. Another, maybe a PIM model could be in WRF-Hydro as well, or some other kind of model swap, who knows. But this is a system for framing the hydrologic modeling and connecting it with the atmospheric and weather modeling. So what we're doing is to connect weather on the top left of this diagram, weather modeling, which is going to be the high resolution rapid refresh rainfall forecast, to land surface modeling. This is NOAA-MP or other land atmosphere models, VEC or whatever. Then to river routing, and we're using the RAPID model that was developed here at UT Austin by Cedric David that was specifically designed for routing water on top of the NHD+. We have previously done this for the Mississippi Basin, for all of the NHD+ reaches in the Mississippi Basin, and we have now succeeded in doing that for the whole continental United States. So what we have done is to take the data for the USGS water resource regions in this area. We've built conversion files that take gridded land atmosphere modeling and convert it to the catchment basis that we have for routing water through the stream network. We have driven that with inputs from the weather model and land atmosphere model in WRF-Hydro and computed flows across the whole continental United States in the 2.67 million reaches. So it is possible to do what we said we were going to do. The Weather Service is supporting us by providing real-time forecast services initially just in one region, which is on the lower right-hand side, Water Resource Region 12 here in Texas, and later they're going to expand that for the whole country as part of the NFIE, so that the forecast being produced by the NFIE experiments can be compared with what the Weather Service itself is producing. Another thing that we're doing is to be able to do soil moisture mapping. So as part of land atmosphere modeling and as an extension of the NASA land data assimilation system, we are calculating soil moisture continuously through the country. And what you see here is a map that's created each day using NASA services for soil moisture information from the land data assimilation system. And we're going to update that map using the NFIE. This is a map of showing the anomaly between the difference between today's value and the average at each cell on each calendar day that has been calculated in the past. And so in this way we can compare the present with the past. This work is being done by a PhD student, Gonzalo Espinosa, here at UT Austin. And Gonzalo has also been able to calculate the statistical properties of the soil moisture produced by the NLDAS model on every cell for every calendar day for 30 years. And so for the current value, you can compare the current value with the past values. So red here means there's a low percentage of current soil moisture compared with historical conditions at the same location and calendar day, and blue means it's high or wet. The graphs on the right-hand side are a time series service of what the actual soil moisture level computed coming in from NASA. So 220 here means 220 millimeters in the top 1 meter of soil, and the top right-hand side is a histogram that shows, or a cumulative frequency function that shows where the current soil moisture value is in relation to the probability distribution. Now the purpose of this soil moisture map is to be able to examine the hypothesis that there's more runoff coming when you've got high soil moisture currently prevailing than when you've got low. So if we have a certain amount of rain on the red, we would expect less runoff than if it occurs on the blue. Another system that's being used is from the European Centre for Medium-Range Weather Forecasting. This is called the Global Flood Awareness System. And it's developed jointly between the European Centre for Medium-Range Weather Forecasting and the European Joint Research Commission. And I want to turn over at this point to Jim Nelson, my colleague from Brigham Young University, who's going to provide the commentary on this on these slides. Jim? Well, I guess I'm not hearing too much from Jim, so maybe I'll provide the commentary. So what you see here is a 15 days ahead ensemble forecast with 50 hydrographs for each location. And the colors here, yellow, red, and purple, represent the different risk levels for flooding in a particular area. And what Jim and his students have succeeded in doing is they have adapted this for application in the continental United States. This is the same kind of thing being done for Water Resource Region 12, and they've got a system that they've developed called TEFIS, which provides a web interface to the simulations. And this is 67,313 NHD plus reaches, and for each of those reaches, what's going on is the calculation of an ensemble of 50 forecasts. And if you look at the horizontal axis here through time, this is January the 13th was when this forecast was produced, and it's anticipated that actually in the period just coming up in a few days' time, there's going to be a significant amount of flow here, and in fact it's looking kind of like rain today, so perhaps they're right. Now, I do not know whether it's possible to forecast rain and flow 15 days ahead. I guess that's one of the things we're going to be able to test in the NFIE, but this is a system that we're leveraging from Europe that helps us to do that. And so for each of these NHD plus reaches, this is for a particular one, reach catchment 5592203, there is an ensemble forecast with 50 hydrographs and the mean, minimum, maximum standard deviation, and so on. And so we're dealing with ensemble forecasting, flow forecasting for each location. Now, if you've got that information, the next question becomes, can we then translate that into river channel information, real-time flood inundation mapping, and so on? Now, you'll see in this map I've got an arrow that goes horizontally from the NFIE-Hydro to NFIE-River that indicates that connection. And I've got another one that goes diagonally directly to the NFIE-Response that says that if we don't have the river information, then we're just going to go straight to the response system to do the flood forecasting or flood warning, and I'll explain how I think we can do that later. Now, for the river mapping, the USGS and the National Weather Service have a high precision mapping program that they operate now at quite a few hundred locations across the nation, where there are USGS gauge sites and National Weather Service river forecast points. This one here happens to be the National Weather Service forecast point at Onion Creek at Highway 183, and there's a elevation scale that you can see on the left where there's two elevation scales. One of them it says 482, 481, and so on. That is elevation above geodetic datum of the water surface, and the one on the right is 39.3, 38.3, and so on, and that's the stage height in the river. And so the National Weather Services uses the right-hand side scale, the stage height, to issue flood warnings, and FEMA uses the water service elevations to establish regulatory elevations for housing. So we need both of those scales. When you go to this map, and the link is at the bottom of the page, what you see if you run your cursor up and down the left-hand side is the map goes in and out. It sort of shrinks and swells, and the colors in the map represent the different depths of flooding as shown on the scale on the right-hand side. So these maps exist in quite a few places, and this is an example of their existence in North Carolina. North Carolina has an absolutely marvelous floodplain mapping program, the best in the country, and they have statewide flood mapping, but in regulatory mapping, but they just have this program that you see here for the data at the gauges. So you can see a gauge there near the city of Burlington, and there's another one somewhere upstream off the map, and there's another one downstream somewhere off the map. But clearly, to fill in the whole landscape of flood mapping, we need something more than flooding at gauges up and downstream of USGS gauges. What the North Carolina Floodplain Mapping Program has done is that they have HEC-RAS models for large areas of their state, and they have 5 recurrence intervals, 5, 10, 25, 50, 100, and 500 years. They've calculated the flows, and they've calculated rating curves for those flows, and you can see a flood rating curve on the lower right-hand side here relating water surface elevation above geodetic datum and discharge. This is in the Tar River, and they've also got the cross-sections at those locations, and they've extracted 300,000 of those cross-sections to build a statewide river mapping system. And so what they do is to interpolate between the gauges to get real-time information from about tens of thousands of locations or hundreds of thousands of locations, and they actually have a map that's 10-foot square cells in the floodplain to look at the risk for flooding of people and infrastructure all across their state. Now, North Carolina is the gold standard. Not all the states can aspire to what North Carolina has done. So if we have such a system, we've got cross-sections at lots of locations, we can actually do the routing in a regional way. And I have a colleague, Dr. Ben Hodges, here at UT Austin, who has been working on that subject. So take it away, Ben.
All right, thanks. So the issue that has been in the past is that we look at the network and how many rivers are in there. It has seemed impractical to run the real dynamic equations, that is the St. Venant equations, that are the river flow models. But what we found is when we talk to people who work in computer chips and computer chip designs, they have circuits with 1 billion transistors, and they routinely will solve circuit problems overnight. In fact, one of the things that they have to do in the design is every time someone tweaks the design, they have to rerun the circuits. So we've been working with some ideas that, that show that we don't actually have to simplify our equations. That is, in the past we've used diffusive wave or kinematic wave models, and that reduces the computational burden. But at the same time, when you use these models, you only get flow rate, you don't get flow rate and height. But what we found is we can indeed solve the full St. Venant equation. Let's go to the next. And we have a model now called SPRNT. It's the simulation program for river networks. And we use some of these ideas from chip design in order to make a model that runs really fast, so hence the name. And so the problem now has shifted, is that we know that we can actually solve the river network, but the challenge is that we need river geometry. If the river geometry isn't correct, it's difficult to get the unsteady flow and depth predictions correct. So therefore, we need on a national scale to have cross-sectional area versus the depth, the perimeter versus the depth, and the bottom slope and the channel roughness. These are your basic inputs to the St. Venant solution.
So here's what we've been doing to extract that information here in the local area in Travis County, which is where Austin, Texas is located. So we have lots of HEC-RAS models here, and this is for one watershed, Onion Creek watershed. There's about 20 individual models, and these are the cross-sections coming from those models. And you'll see that they stop at the county line because that's how floodplain mapping is done. It's done by counties. So, well, I guess hydrology doesn't worry about county lines, but floodplain mappers do. But in any case, you can see that there's lots of cross-sectional information available here. It's all in these little individual HEC-RAS models, and we have to extract that out, reverse engineer that, and then put them into a national repository, and we're going to use HydroShare to do that. And we're going to design a data structure for putting that information there so that it'll be stored in a nationally consistent manner. And we're going to collaborate with the North Carolina Floodplain Mapping Program in doing that, because they've really thought deeply about how these problems can be dealt with on a statewide scale already. And I want to acknowledge the contribution of Jing, one of my master students who produced this map. So with this kind of intelligence, you can start to work with regional kind of map modeling like what Dr. Hodges was talking about. You can also use the HEC modeling system itself, because there's a Hydrologic Engineering Center system called real-time simulation that can take HEC-RAS models and HEC-HNS models and build them together. So it's possible to test an engineering solution of the usual kind as well as this rather large-scale SPRNT and other kinds of solutions. Now let's continue now to the fourth component here called NFIE-Response, a wide area flood planning for flood emergency response. And we're working here with the Austin Fire Department, and I want to introduce my colleague, Harry Evans, who's Chief of Staff of the Austin Fire Department. Harry, can you tell us a little bit about what you do as Chief of Staff?
Sure. Hi, my name's Harry Evans. As Dr. Maidman said, I'm the Chief of Staff of the Austin Fire Department, and my job is the day-to-day operations of the department. So Dr. Maidman and I, for the last several months, have been working together with discussing with him the needs of the emergency response community and steps that we would take to educate the public, steps that we would take for emergency planning, and steps that we would take for the response mode when the flood is actually happening. And so he and I spent a tremendous amount of time together, and I'm excited about the opportunities that we might be able to further enhance the things that we do.
And the fact that we got together was the result of the Halloween flood that happened on Halloween 2013 and Chief Evans was managing the Halloween flood. So can you tell us what happened then?
Well, that particular flood was in the Onion Creek watershed, which is in the southern part of Austin, southern part of Travis County, and the northern part of Hayes County. And there was a significant amount of rainfall that fell in the very western edges of that, unbeknownst to our flood early warning folks within the city of Austin. And about 5 in the morning, that water was upon us in what seemed to be just minutes. And we weren't really prepared for that. We've been running water rescues all night because we had flooding around the city, but it wasn't out of the norm of what we've handled in Austin just because of our proclivity for flash flooding. But when that water was on us, we had hundreds of people stranded in their homes, people on roofs, and we weren't able to evacuate them ahead of that water, and that was a big concern for us. And it seems like there's knowledge out there and there's information out there that we could have used had we known it was there.
So one of the things that your department does is do swiftwater rescues. I guess this is the vehicle that you use for that, is it?
Yeah, that particular, if you're looking at that screen, that particular vehicle that you see there is one of our special operations boats, and we put 4 firefighters in there, swiftwater rescue technicians, and then they've got a military spec Zodiac swiftwater rescue boat. And so that's that particular setup, that particular response vehicle is used to conduct swiftwater operations. It's one of many of the different types of things that we would do in a flood.
And did you do swiftwater rescues in the Halloween flood?
We did, absolutely. Yeah, we had the Halloween flood really outstripped the resources of the Austin Fire Department. I think that, we're the 11th largest fire department in the United States, but you could be FDNY, the largest fire department, and you can find an event that'll outstrip your resources. And so we've got to get better about planning, and we have to get better at response, and we have to get better at educating our public that if the public is more resilient and they're more adapted to flooding and flooding issues, if they're able to take care of themselves, that significantly reduces the load on any one department. And so there's lots of ways that we can leverage other agencies, public education. There's many approaches, I think, that we can take to better do the things that we're charged to do from the emergency response side of the fence.
So in working with Chief Evans, there's really 2 different pieces of this. One is, what do you do when a flood is happening? And the other is, what do you do ahead of time to sort of prepare yourself? And you may know that if you make an emergency call to your home and ask for an ambulance or a fire truck, police to come to your house, there is actually literally a GIS point that's associated with your house. This happens to be my house, actually. And so when the person is dispatching the emergency response units to your house, they're looking at a map, and on the map there is a dot, and it's called an address point. And in Travis and Williamson counties here in Texas, there are 495,000 of these address points that are established, and these are set up when the lots are legally platted. So if you look at the distribution of these points, it gives you a sense of where people are and where they will have to be rescued from in the event that they're flooded. And so what you can do is to say, okay, I've got the address points, and here is the intersection of the address points and the floodplain in the Onion Creek area. Can you describe what happened at this particular location?
Sure. And so what you see in red is the level of inundation that the flood caused, and then the yellow points are the homes. The situation there was, because it was at 5 in the morning, most people were at home at that particular time, and so you have to assume that entire population is stranded in their homes. And then we geographically divide that into divisions, and we assign a certain number of firefighters to each division, and then our job is to get people out either via helicopter, via swiftwater rescue boat, depending on the water type and the hazard risk. We might be using a water evacuation boat. We may be using high currents vehicles. It just depended on their particular situation as to how we got them out of there. What would have been helpful was to have been able to know that earlier, say at 3 in the morning, and we could have done some reverse 911, some other public notification, and maybe got those folks to evacuate prior to the water getting into their homes and blocking their egress or the roads that led out of that subdivision.
Now, 700 homes flooded and 5 people drowned in that flood. So you can take those kinds of maps and make them regionally for Williamson and Travis counties, as you see here, and you can identify from that where are the likely areas of highest risk or highest vulnerability. And so I have summarized these here by HEC-12 subwatersheds, and in fact the largest risk area is the Onion Creek area in the lower left of the picture, and it has 1,981 address points that could be flooded. There's one just north of the Colorado River with 1,784. You can see this is almost 2,000 homes. Now, what do you do with 2,000 homes? I mean, it just starts to, you get a sense of the size of the problem here. About 2.5% of the homes in Austin are in the floodplain. Now, if the people are going to get out, they have to use the street system. And so another thing that we can do is intersect the flood inundation map with the street system, and we can delineate how much of the street system is flooded in an extreme flood. And this is another map for Travis and Williamson counties that shows those numbers compiled according to HEC-12 subwatersheds, and in fact in the Onion Creek area about 52 kilometers of roads would be flooded. Now this map is somewhat different than the one you saw before because there's quite a lot of roads flooded in northern Williamson County, but that's largely rural land. So even though the roads get flooded, there's not so many people there. Whereas in the lower part of Travis County, it's this road's getting flooded and people are there as well. So there's sort of a double whammy there. So finally, how are we going to deal with flood services? Some of you may know that CUAHSI has been working for a long time with the US Geological Survey and with other organizations, the Open Geospatial Consortium, World Meteorological Organization, and so on, to establish what is now an international standard for the transmission of water resources time series on the internet. This is called WaterML2, and what you see here is a series of time value pairs that is the way that real-time water information is transmitted now in the United States from the Geological Survey. They have a 24/7, 365 service all across the country for flow information. It's remarkable actually that we've got such a system. What the Weather Service is going to do as a part of the NFIE is that they are going to start publishing similar kinds of services for their forecasts. So at the 3,600 forecast points that I mentioned earlier, they're going to start publishing their estimates of the inflow to the channel, the mean aerial precipitation, and the stream flow at the forecast point. And those will be associated with the Hydro outputs that are coming from NCAR and going into the Rapid model or other models that look at the river system so that we can compare the forecast values with what's actually occurring. So what's going to happen is that the Weather Service is working to acquire data from its 13 community hydrologic prediction system instances in the different regional forecast centers. Those are going to be centralized at the University of Alabama, and they're going to be published from there. There's going to be a data publication service in WaterML2, and this information service is going to be also provided to the National Water Center. So this is the first time that the Geological Survey for the past and the present and the Weather Service for the present and the future will be publishing their water information in the same format at the same locations, which is kind of a milestone in itself, I think. And finally, if we can align the forecast from this detailed system with what's being done at the less detailed system, at the regional system, we can then say, if we've got an ensemble flood forecast or if we've got a high level of water forecast, we could color in this little flood zone that's in the elementary reach catchment that I talked about at the beginning of the presentation. Green if it's okay, orange if it's warm, if it's rising, red if there's an action level. And let's imagine now that this map is being able to, those colors change through time, and they're populated for all the reach catchments in the watershed and not just for the one that you see at the outlet there. And this map, we can bring the cursor forward into the future and get a sense of what the risk level is and where it will be spatially as the flood is anticipated to happen. Then we get the situation that Chief Evans was talking about, of being able to pre-position resources and get people out ahead of time and so on. And so what our intention is to go straight from the ensemble flood forecast to this little polygon coloring system here in the event that we don't have detailed river information and river mapping capabilities, and in the event that we do, then we go through the NFIE-River to be able to produce expected inundation polygons. So that's the general plan, and so my assessment is that the NFIE-Geo, which is the Geospatial Information Support System, I think is really solid. And this is federal information, it's clean, it's public, it's going to be provided, no question about it. NFIE-Hydro is a work in progress, but I think it's achievable at the Summer Institute. In other words, the idea of higher spatial resolution, near real-time flood forecasting, we're already far enough along now that I believe we're going to get there at the time of the Summer Institute. The NFIE-River has some good input information, but in some regions, but it needs a national structure and data. In other words, we've got some work to do here to sort of systematize that. The NFIE-Response needs further development. What you're seeing here is just the result of some preliminary discussions with myself and Chief Evans, but we want other groups to get involved as well, and other first response communities and other student communities around the country so that we can engage them in this process too, not just here in Austin. And this NFIE-Services thing is just beginning. As you can see, the Weather Service and the Geological Survey are just getting themselves together. So your contribution to advance these components is very welcome, and that's the conclusion of the formal presentation.
Well,
Emily,
I think
you want to take it?
we can open this up to Q&A. So any participants who have questions, please type your question into the chat box.
So Joseph Gutenson is typing, and let me just introduce Joseph. So Joseph is a grad student at the University of Alabama, and he is going to be helping with the coordination of the NFIE at the National Water Center this summer, along with Fernando Salas here from the University of Texas. And in fact, we're teaching a flood forecasting class here jointly between the University of Texas and the University of Alabama this semester to try to develop the preparation for the NFIE. Okay, this is for Dr. Maven. With the point layer describing the addresses, what underlying data accompanies these points? There isn't very much at all, Joseph. Basically, the first response community in your area, in Tuscaloosa, for example, just has these points, and it's just basically a point and an address. Now, if there's a landline phone at the same location, then the landline phone is associated with the address as well, so that if you call in on the landline phone, it automatically knows which address that you're going to, or you want to go to. If you call in on a cell phone, then it has to geometrically locate itself to find out which location that you're at. But is this for businesses as well? Yes. I mean, well, that would be true, right? Yes. Any other questions? We've got some people typing here, so let's just wait and see what comes up. Is an involvement from the Joint Research Centre in Europe, is there involvement from the Joint Research Centre in Europe with the NFIE? Yes, that's true. So the European Joint Research Centre is located in Ispra in northern Italy, and that is the unit that's been doing the hydrology modelling component of the GLOFASS system. There's a person there by the name of Peter Salomon and some colleagues that are involved with that. So they're keen on working on global flood forecasting, and there's actually a meeting in May for a global flood system, and the European Joint Research Centre is engaged with that. So we have Solomon Vimal and Joseph Gutenson typing. Come on, guys, ask some questions. We need a few more. There's 81 people on this call, so there are a few more people that could ask questions. Okay, this is Obide from Alabama. If anyone has some contribution to make, who would be the person to contact? That's a good question. Emily Gosling, do you want to speak to that? Emily from CUAHSI, who would they contact?
Contact Emily Clark at CUAHSI. Her email is eclark@cuahsi.org. She would know more, and if you could be more specific about what contribution you'd like to make, that would also help, because this is such a large and varied group of people working together on this project.
You want to say something about the call for proposals, Emily?
I do not have that information. That is with Emily Clark and Rick Hooper as well. I'm sorry about that.
So there's going to be a call for proposals shortly to participate in the NFIE, and this lecture is meant to help frame that. So Solomon says, I'm a student in Europe. I was told that for now I'm eligible for the summer school, but there's no final word on that yet. Yes, that's being worked through the Weather Service. They have to go through their legal system to check things off. We're confident that it's going to work out, but we don't have the final conclusion on that as yet. Okay. When will the student application for the Summer Institute start and end? The application is going, the deadline is going to be in February, I believe February the 15th. Although that, I'm not certain that deadline's been absolutely set in stone as yet. So what we're doing right now is we're in the process of drafting the call for proposals, and when that's finished, we'll establish the deadline for the time. Many areas of the US have only the NED available for elevation data. How do you foresee this being overcome should the NFIE be implemented? Dan, that's a good question. So basically, about a third of the country is covered with LIDAR, and about 2/3 is not. Now, the NHD Plus has been built from the National Elevation Data Set. It has not used LIDAR, at least in only a very small way. And my assessment is that the National Elevation Data Set is okay for hydrology. It's where it falls down is for hydraulics, for the river channel stuff. So what we're going to do in the areas where just the net is available is we're going to use the NHD Plus catchments and the ensemble forecasting that's done on the hydrology side, like what I was illustrating from ECMWF and others, to directly intersect with the National Flood Hazard Layer so that we can say, if the forecast is, we've got a 10-year flood forecast here, that means high risk, and just use the static mapping that's already in the National Flood Hazard Layer to be able to create the risk zone. So we will not then be held up by the fact that the LIDAR data and detailed information for river modeling isn't available in many locations. Has Dr. Hodges been using the NED with SPRNT, or is he using LIDAR? Right now, we're just doing test cases with SPRNT, and some of the test cases have been done using LIDAR, for example, within the city of Austin, to verify that the solution matches that which is given by HEC-RAS. And what we are hoping is that as this effort to systematize the cross-sections and their archiving on a large scale spins up and becomes more widespread, that we'll be able to run SPRNT on larger areas, which we haven't been able to do up to this point. So I see here something that says Jim Nelson. Jim, do you want to make some comment? Okay, so Jim has some audio problems, so he's not able to join us as yet. but we want to really appreciate the contribution of Jim and his students. He started working at the international level using the ECMWF and RAPID systems in basins in Colombia and Dominican Republic and so on. Jim is asking, when's the next webinar and what will be the topic? So the next webinar is going to be on Wednesday, February the 4th, and it's going to be led by students, by Joseph Gudenson actually, and by Fernando Salas, and students from here and Alabama and other places are going to talk about the projects that they are now working on and formulating so that other students in other locations can get a sense from students that we're in contact with about how they could also formulate projects that could be worked on for the NFIE. We're hoping that this would be a team type of effort so that there'll be students working together who from different universities. For example, Cassandra Fagan here in Austin and Madeline Merrick in Utah have been talking about working together on with Chief Evans on the flood emergency response work. So a team doesn't have to be from one university, it can be from several universities. So up to this point, the webinars have all been led by the faculty, but next time the webinar is going to be led by the students and in fact coordinated by the student coordinators who are going to lead the Summer Institute in Alabama. So I guess Joseph is making another contribution here. Whom the FEMA will be working on NFIE? Will any of the hazards group be participating? Sorry for all the questions, that's fine, don't worry about it. So the key parts of FEMA that we're dealing with now are the part that deals with the National Flood Hazard Layer, which is the geospatial component alone. If we need to get the hazards people involved, we can do that too. That's called Hazards of the US, I guess. It's a computer data system that comprises impact information of what's the economic cost when flooding goes into certain areas. And we haven't worked, well, we here in Austin haven't worked much on hazards as yet, but it would certainly be a good thing to do. Dr. Mayman, in your opinion, when do you expect a global NFIE to materialize? That's a good question. When I first proposed the National Flood Interoperability Experiment, I had the idea that we would learn from this at the national scale, and then we would engage the World Meteorological Organization and others like the European Joint Research Commission and some national agencies in different countries. And next year we would have a global flood interoperability experiment. But actually a curious kind of thing has happened, that the global flood awareness system being used already in the United States is in effect informing us about how things can be done differently in our country using technology that comes from Europe. So in a sense, the global flood interoperability experiment is already happening. And the technology and the methodology which was presented here for the Water Resource Region 12 by the group at BYU has been previously applied by them to several areas in Central and Latin America. And so there is, in a sense, already a global flood interoperability experiment going on in parallel with and interacting with our national flood interoperability experiment. While Solomon is typing, do you have any more comments you want to make, Chief Evans?
No, I think I'm good at this particular point. I'm just looking forward to engaging more and at least working as a liaison between the public safety community and the academic community.
So who's working on this in Europe? Institutions, people, any names? So the main group that we're working at the academic level in Europe is the UNESCO IHE University in Delft. And so Jim Nelson and I and Dan Ames from Brigham Young went to Delft last May. We presented a day-long program about water information exchange and so on. And we hope that that university, which has over 200 graduate students from the developing world, can become kind of an anchor for this sort of work in the developing world at the international scale, rather than us having to try to do that from the US. So there's a person, Dimitri Solomatin, who's in charge of the hydroinformatics program in Delft. That's the group that we're working with. Of course, the European Centre for Medium Range Weather Forecasting in Reading in London, and the European Joint Research Commission in Ispra in Italy. Also, there's a large number of international hydrology programs and data programs that have now been centralized in Germany at the Bundesanstalt für Gewässerkunde, the German Federal Institute for Hydrology in Koblenz, and the Deutsche Wetterdienst, or German Weather Service, in Offenbach. They have the Global Precipitation Climatology Center in Offenbach and the Global Runoff Data Center and the Terrestrial Hydrology Network in Koblenz. And so we're interacting with them as well. So this is part of the work that we've been doing with WMO for quite a few years now because of the WaterML, and we're engaging with the WMO and its institutions in Germany to support this work as well. So Solomon seems like he's a pretty active guy. I think he's going to be going to be a grad student at Utah State University or something like that. So, yeah, well, we very much want to involve Europe. And as you can see, there's a pretty sophisticated system that the Europeans already have. And I really like their methodology, actually. I think it's something that we could significantly learn from, even if we don't use their model. If we just learn from the way they're doing things, I think that will be helpful.
Okay.
Well, do we want to declare victory here?
Questions, you can try now or forever hold your peace until next webinar. Otherwise, I think we will close this down for today. And the next webinar is, David, can you repeat that? February 4th at 3 o'clock?
Yeah, Wednesday, February the 4th at 3 o'clock Eastern Time. And it'll be led by Fernando Salas from Texas and Joseph Goodenson from Alabama, grad students.
Okay. Well, in that case, thank you to everyone for coming, and we hope to hear you. We hope to see you on the webinar next time. Thank you, and thank you,
Bye-bye.
David.
You're welcome. Bye bye.